The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Hello, welcome to 2003. My name is Sanjay Sarma. I am a professor in mechanical engineering and I'm the instructor for this course. It's a great pleasure to have you all in this class. Unfortunately, as you can tell, I am not in Boston. I'm in India right now. I was supposed to teach a class in India because I thought I'd be on sabbatical this semester. As it turned out, I'm teaching this class. I'm going to fly back this Thursday, and I'll see you in person on Monday. But I have taught 233 a couple of times before. It's a great pleasure. So welcome. 003 is probably, in my opinion, the most fun class in the mechanical engineering curriculum. It is all about stuff that moves, which is what mechanical engineering is all about. So what I'm going to do today is I'm going to go through the class outline. You have with you the class outline in terms of a definition of the class, the schedule, the instructors, contact, etc. But I'll just go through it in slides, and then we're going to do two other things. After I introduce you to the course, we're going to have a quiz. But don't worry, this quiz does not count for anything. It is to check how well you know your prerequisites, and it's also to check how well you understand what we will be doing in this class. So there's a portion of this quiz which you should not be able to do, and if you can, that's great. And it is an indication of the sort of problems that you will learn to solve in this class. So anyway, and the last piece, I will begin actually getting into the course, and we will start doing kinematics, which is the topic of the first lecture. I'll tell you what kinematics is in a minute. So don't worry, let's get going. I'm very informal. I'm going to cold call you guys. I'm going to make sure that you speak. This will be a very interactive class. If I were here right now, I would have cold called someone already. And I think we'll have a lot of fun. We have a terrific staff of other professors who will be doing recitations and teaching assistants who will make this a good class. Now, this class has over 120 registered students. So it's going to be a very tightly run unit. And we will have very precise schedules. And you need to try and play ball because we don't want to fall behind. It becomes a bit of a mess. And the instructors and the TAs all are, we're all raring to go. We have, first of all, recitations in this class. Recitations in 2003 are important and mandatory. In other words, you must show up. Attendance will be taken. And in fact, you will see later that a part of your grade will depend on recitations. So you must show up. It's not optional. If you can't show up for some particular very important reason, make sure to talk to your recitation instructor and tell him why. One of the key things about this class is that we will have a section on MATLAB. MATLAB, as you know, is a mathematical programming tool that's very important in dynamics and controls, and it's actually very important in engineering. And MATLAB, I believe, was founded by an MIT alumnus as well. That will be taught by Professor Peter So. And Professor So's contact information is also listed here. And if the instructors could wave so that people know who they are, that'd be great. Excellent. So that's the teaching staff. You'll get to know us all very well during the course of the semester. Perhaps equally, if not more important than the professors, are the teaching assistants. The head TA is Mr. Ajay Deshpande. Ajay, I hope you're waving. Ajay is going to be very key because he's going to run a lot of the review sessions, and he'll be kind of quarterbacking the homeworks, etc. And his room number is 35-010. That's the same building that I'm in, but in the basement. And his email address and telephone number below. Mr. Faraz Eid, who's the other TA who will be doing the bulk of the non-MATLAB portion of this class. Between Ajay and Faraz, they'll be in charge of all the homeworks and a lot of the organization of the class, and between the instructors and these two gentlemen, all the reviews. And finally, for the MATLAB portion, we have Mr. Daekun Kim, who is going to be TAing the MATLAB assignments and so on. And then we have graders whom I won't name, who will be helping us grade the homeworks, both in MATLAB and in the actual course, in the actual dynamics part of it. This is a pretty heavy course. We have 2 lectures, and the lectures will go 9:30 a.m. to 11 a.m. on Mondays and Wednesdays. They are going to be obviously in this room, but as you can see, access to this room is limited because you can only come in through the front, and it's a little disruptive. Again, we're very informal, so if you are late, that's fine, but please try and be on time. And we will get going at about 9:35 sharp. We have a lot of material to cover in this class, and we'll be going at a fast pace. By the way, one of the things about the way I teach is I encourage people to interrupt me. If you have any questions, raise your hand, and I'll be asking you questions. I'll be asking the audience questions, answer them, and if I find someone particularly unwilling to answer a question or unwilling to volunteer to answer, I will call you out. So we'll all get to know each other very well. MATLAB sections, there'll be 4 MATLAB sections. Fridays, all 4 sections are Fridays, and the 4 contiguous hours between 1 p.m. and 5 p.m. They'll all be in room 343 of building 3, and Professor So will conduct the MATLAB section. After the slide, I'm going to request Ajay to pause this video, and perhaps Professor So can spend a few minutes describing MATLAB, what it is, and how it's going to be run, and what he expects from you. Some of these sections will be tutorials or recitations, and some of them will be lectures. Professor So will describe that in a minute. And then finally, the actual recitations for the material that I will be covering in class. There will be 6, and you've all registered for these 6. 4 will be taught by Professor McCris, and 2 will be taught by Professor Patrick Kalakis. And we're going to try and balance these recitations. We're looking at the compositions right now. Strictly, we need about 24 to 25 in each recitation. We don't encourage you to change. If you have to, please put up your hands, or actually come to the recitation instructor. Actually come to Ajay as when we pause in a minute, and we'll try and sort it out. But you must try and stay with your original recitation unless it's something very, very important. It's really, as I said, this class is going to be a bit of a circus if we have too much change. So please try and cooperate. Excuse me. And then we'll also have office hours. We'll announce them very shortly. In fact, by the time you see this video, we might have them all cleared up. And I'm going to ask Ajay to pause after this and announce the office hours as well, write them on the blackboard. So 3 things now. Ajay is going to pause this video. Professor So is going to describe the MATLAB portion of the class. We will sort out the sections right now. And finally, Ajay will announce the office hours. So we're going to pause now. Okay, we're back. So going on now with the actual material. We have 2 textbooks. There's only one that you really need to buy. The other one is a reference. You can get it from the library. If you want to buy it, it's a good book to have. The first is by Professor Jim Williams, who is a professor in our department and a very well-known author and engineer. And it's an excellent textbook. Now, we will be following this textbook in a loose way. We will have reading assignments, which we encourage you to read. Our notation is slightly different, but the problem sets will, many of the problems will come from the textbook. Not all of them, but many of them. And it's just a fantastic book to own. because it addresses a lot of questions in great depth. But the way we're going to teach this class will be slightly different in the sense that the notation will be different, and the way we're going to parse the topics will be different. But there's a one-to-one correspondence between what we cover and the textbook, although the sequence is off. So that's the textbook. The other book that the rest of the world uses is something by the name of Engineering Mechanics and Dynamics, which is by Miriam and Craig. The way we teach dynamics here at MIT is not, it's for MIT students. It's not simplified. It's not, we don't dumb it down. And we're going to teach it in a way that is profound and interesting and exciting, and the way we feel MIT students should know it. Miriam and Craig, a great book, by the way, just a very good book, teaches it in a slightly simpler way. So it's a good book to read, but if you can't depend on it for everything we will cover in this class. We will take the differential equations approach to dynamics, and Miriam and Craig takes the instantaneous approach to dynamics. I'll explain what that is when I'm back in town. The prerequisites for this class are 801 and 1803. 801 is and 1803 are basic courses in math and physics that you've taken before, and we will pick up on a lot of that stuff, and we will proceed from there. But there isn't necessarily, once we start the class, we will very rapidly start doing stuff that isn't covered in those classes. There'll be a few terms like the parallel axis theorem, physical to MA, etc. Conservation of angular momentum, conservation of linear momentum, that we will pick up on. The physics is obviously the same. It's just that we're looking at more interesting and complicated problems. But you need to know this stuff, and we will use it as the foundation. And finally, we're going to be using the Stellar website. All homeworks will be posted on Stellar, and all solutions. I'll talk about homeworks in a minute. We will have exams, obviously, you will get in class, but the solutions to the exams will be posted. Schedules will be posted. Class notes that Ajay and I make up will be posted. Example problems. So it's going to be very key, and we encourage you to refer to that slide, excuse me, on that site on an hourly basis. No, I'm kidding. Look at it at least a couple of times a week, and we might send you email reminders as well. But do keep looking at that website. It's an important website for this class. Okay, so that's supporting material. Problem sets are a key part of this class. You will need to pay a lot of attention. They will go out usually on Mondays, and they'll be due the following Monday. There will be exceptions. The exceptions will be, for example, when we have holidays on Mondays, or when we have an exam and we have to, we have certain rules of what we can make due on weeks of exams and so on. So we'll follow those, so we might bend that a little bit. But the problem set goes out on Monday, and it's due back at 9:30 a.m. the following Monday. We will not accept late homeworks unless it is an extraordinary event that prevented you from doing the homework. And we expect a high level of honesty. That should be honesty, not honest. Groups are okay, copying is not. And we will disallow homeworks that we think have been copied, and we're going to be fairly diligent about it. So this is going to be a fun class, folks. You got to take it seriously, and we'll all have fun, but we'll have certain rules that we expect you to follow. Two tests in this, two midterm exams. The one is on the 24th, and one is of October, and the second is on the 19th of November. And 1-3 are final exam, which will be on a date that the registrar hasn't announced yet, but will be announced, very shortly. All exams, including the final, will be closed book. You will not be permitted to bring in a textbook, but you will be permitted crib sheets. The first exam, 1 sheet. Second exam, 2 sheets. Final exam, 3 sheets. So that's the tests. Okay, this is the way the grades will be broken out. 35% of the grade will come from classwork, that is outside of exams. And the way that breaks out is 10% for homeworks, 7% for recitations, 15% for MATLAB, and 3% for class participation. So what is class participation? So here's the way we do class participation. You might consider what I'm going to tell you bad news, but I actually think it's good news. You guys pay a lot for your MIT education, and we want to make sure you get a good education, right? So we're going to have snap quizzes, 5 to 10 minutes on and they're snap, so there's on random classes, during random classes. And I might, in the middle of a lecture say snap quiz. And the quiz would most likely be written on the blackboard, and all you do is have a go at it. Now, we won't grade the quiz beyond giving you a 0 or a 1. So it's as much a metric of attendance, and for us, a metric of whether you're getting the material or not. So we're not trying to really kind of treat it as a quiz. But we will have these snap quizzes. You can miss 1 or 2, you'll be fine, but you can't miss a lot. And we'll also keep track of who's talking in class. We really want you to be communicative. We want you guys to go on and become the leaders of industry, not some Harvard MBA who didn't go to MIT and just wants to give you orders. So we want you to be articulate engineers and leaders. So that's the 3%, and we'll take that very seriously. And 7% from recitations, and that also has to do with your participation and perhaps more importantly, your presence. So there will be attendance in recitations. 2 midterms, 40% each. It's 20% each, and they'll be conducted in this class, during the class, and 1 final 25%. One comment here is that this class, we cover a lot of material, MATLAB, there's a lot of activities, and steadiness pays off. So you need to be steady. The final exam is only 25%, which means that you can't redeem yourself, just by nailing the final. So you need to really go at it. It's a bit of a marathon, and you need to join us in the kind of like a triathlon. Okay, so I'm going to pause now, and now we will deliver the snap quiz, and then Ajay is going to give you about 20 minutes or so for the snap quiz, and then he's going to restart the video, and we will get into the basics of the class that we want to cover, which will set up my lecture when I return on Monday, next Monday, when I return from India and I'm here in person. Okay, so we'll pause now. Ajay, go ahead, pause the video. Okay, now we are going to talk about the class, and we're actually going to get into our first lecture, the first content of the class beyond organizational stuff. So this class is about dynamics. So what is dynamics? Dynamics is about stuff that moves. If I take my keychain and I toss it in the air and I grab it, it moved. Now, obviously, studying my keychain isn't as important as studying, say, a satellite, or studying the dynamics of a baseball, or studying, a truck and seeing why it vibrates, and when it goes on a road, and how much it vibrates, so that you can design the right shock absorbers, so that you can design the right stiffness for the spring, so that you can design the right damping coefficients in the shock absorber. So this is the essence of dynamics. It's a very interesting topic. As I said, I think it's the most interesting topic in the mechanical engineering curriculum. Although I've also taught 2001 and 2007 and 2008, and I've made the same claim in those classes. But I actually do think that this is the most interesting topic in mechanical engineering. I have just 4 slides with which I'm going to set up the class today. This is kind of the first mini lecture. What is dynamics? All of dynamics can be captured with this one equation. That's it. That's all there is to it. All of dynamics is this. It is Newton's law, and or it comes from Newton's law, Newton's 3 laws, which we'll go into in more detail later. But essentially, force is equal to mass times acceleration. And with this fundamental, simple law, and with math, you can do everything you need to do with dynamics that has to do with rigid bodies. You will do in 2001 and 2002, which some of you are taking, you've seen deformable bodies. But in rigid bodies, this is all you need. And in fact, even deformable bodies use just this plus some constitutive relationships that tell you how much things can stretch, like elasticity and so on. All right. So that's it, folks. So why such a big rigmarole, and why such a big course? Why so many professors, and why is this such a big deal? Well, it's a very important thing for us, but the analysis of this equation of motion becomes difficult when you talk about complicated objects. It's actually not difficult. It's interesting and it's exciting and intriguing, but you can get lost. And so we try and put structure around it, and that structure is this course. So let's examine this. First of all, you will notice that this is actually a differential equation. Why is this a differential equation? Because F is a force, M is a constant, A is actually the second derivative of position, d2x by dt squared. So what we're saying here is F is equal to m times d2x by dt squared. And that is actually a differential equation. The way I've stated it, it's a simple differential equation to solve, and it applies to a single particle, but it is a differential equation. Actually, it's three differential equations, because in 3 dimensions, it's a vector differential equation. F is a vector, it's force. It's got 3 components, x, y, z. A is 3 components, x, y, z, ax, ay, and az. So it's a vector equation, and if you break it up into its component pieces, it would be fx is equal to max, fy is equal to may, fz is equal to maz. That's 3 equations. And a particle in space, in our space, has 3 degrees of freedom. It can move x, y, and z directions. And so you need 3 equations, and bingo, you have 3 equations. They just happen to be differential equations, but they're equations. So 3 equations, 3 unknowns, solve it, you're done. And that's the essence of particle dynamics. Now, the problem is that when you look at more complicated pictures, calculating that A gets more exciting and challenging. And so much so that we have a name for that, and that is called kinematics. And kinematics, as I just said, is simply geometry. That's it. It is motion and geometry. It's got no forces, nothing. It is simply trying to figure out what the velocity of something is and what the acceleration of something is. So you might say, well, that's easy, right? But let me ask you a question. If I told you that the space shuttle was orbiting the Earth at a certain velocity, at a certain distance from the center of the Earth, and I told you that an astronaut was spacewalking on the surface of the space shuttle, and with respect to this, to some reference point of the space shuttle, the astronaut was walking at a certain velocity. And if I said that the astronaut's actually holding a robot, and the tip of the robot is now moving with respect to the astronaut at a certain other velocity, and I asked you, what is the velocity of the tip of that robot? And then I said, what is the acceleration of the tip of that robot? How would you calculate it? No forces, no dynamics, just kinematics. And the way you would do it is, you would do the geometry and try and figure out what the acceleration velocity is. And you know what? You have all the tools to do it right now. You could write down the equations, you could draw vectors, and you could figure it out. And that's what kinematics is. And what we try and do in this class, in the first piece of this class, is going to be understanding how to do that well. Now, if you know what the velocity, the acceleration of that tip of the robot is, then, and you know the mass of that tip is, then you know what the force is, or the force you need to apply to accelerate that tip. And then you can figure out what the hydraulics need to be to generate the force, and what the rocket thruster needs to generate, and so on. So that's why kinematics is at the core of this subject. Now, after kinematics, once you figured out the A part, then you can write down the F is equal to ma equation, and you get a differential equation, and that is called kinetics, which is once you know the kinematics, then relating the kinematics to the force and the mass. You got the kinetics, kinematics, and kinetics together are what we refer to as dynamics. Kinematics is geometry. Kinetic means motion due to force and mass. And together, kinetics and kinematics form dynamics. Now, that's for one particle. When you have multiple particles, for example, if you examine the desk in front of you or the chair you're sitting on, if this desk or this chair was spinning through space, then there are multiple particles, and all the particles are applying forces on each other. And you could, of course, you could write a million F is equal to ma equations and sort it all. It just becomes computationally burdensome. So one of the most utterly brilliant developments in dynamics is that we develop an equivalent equation, which you'll see more of, and don't worry if you don't understand it right now, although you have seen this in previous classes, which is torque is equal to something called the moment of inertia multiplied by the angular acceleration, which are also vectors, and it's for handling rigid bodies. And this moment of inertia is a strange Quasimodo beast, which is hard to explain in a word, but you guys have a sense of it, but we'll explain it in great detail later. And it's just one more equation with which you can handle rigid bodies of infinite particles. And it's pure genius, because what happens is if you take F is equal to ma, that's 3 equations, torque is equal to I alpha, that's 3 more equations, that's 6 equations, and a rigid body in space has 6 unknowns: x, y, z motion of the center of mass, and roll, pitch, and yaw, 3 rotations, 6 degrees of freedom, 6 equations. It's beautiful. And really, once you understand this, you understood dynamics. And so this is what we're going to do in this class. And that, the development of a moment of inertia I to replace thousands of equations for thousands of particles with one equation for a rigid body is just a beautiful, one of these beautiful things that make dynamics such an interesting topic. So with that, let's examine. I'm going to go through, I have kind of a map of the course, and we're going to examine how we're going to traverse the topics in this course. As I said, there are broadly 2 topics in dynamics: kinematics and kinetics. In the handout, which I'll hand out later on, you will see that there's another topic called constitutive relations, which is more important in 2001, but we'll kind of bunch it all into kinetics right now. And first, we will examine kinematics and kinetics for a single particle. Or, I'm sorry, we'll examine it in a different way, but you can examine the kinematics and kinetics of a single particle. You can look at 4 particles or multiple particles. But when the multiple particles reach thousands and hundreds of thousands, and they're a continuum, then you obviously can't write equations for each individually. And if those particles are constrained not to move against each other, we call them rigid bodies. And then you can, you need to analyze the kinematics and kinetics of rigid bodies. It turns out that Lagrange, a scientist who lived several hundred years ago, developed a way in which you can analyze the dynamics of systems, rigid bodies, single particles, complex systems, without teasing apart the kinetics and kinematics. And that's a very beautiful, if less intuitive way of doing things. We'll cover that. And then finally, the whole point of this is we come up with a differential equation. You need to solve it. And in the last part of the class, we will solve the differential equation. So this is how we're going to navigate this. We will do all of kinematics. We will barrel through it in the beginning of this class. That's the first thing we're going to do. We're going to nail kinematics. And we're going to do it in its full glory, 3 dimensions. You will see terms like Coriolis accelerations, centripetal accelerations. And you will completely, when you're done with kinematics, you will be the masters of kinematics way beyond any undergrad anywhere in the world. So we will completely nail kinematics. The reason is that's actually the toughest part of dynamics at some level, of rigid body dynamics. And then we will do the kinetics of single particles. So we'll say F. So now you figured out the A. We'll write F is equal to ma for single particles. We will kind of do multiple particles, but I find it boring, and I'm the instructor, so I can do what I want. I'm not going to do multiple particles because I find them somewhat tedious. But we will do rigid bodies again in a great deal of glory, and we will really understand rigid bodies. Now, one simplification, we will limit ourselves to two-dimensional rigid body dynamics. And the reason is that there's a lot of machinery that goes to 3 dimensions, which you will eventually do in grad school if you want to. You can pick it up, but it's very distracting for a class like this, so we won't do it. That's one compromise we make. Then we'll do Lagrange. Lagrange is kinematics and kinetics all bunched into one group. And then we will solve the equations of motion. So that's what we're going to do in this class. So the way the class is laid out, I don't know if you can, let me just walk up to the chart here. This whole thing is the first piece of this class, the first section of this class. The first half of the first third is kinetics, and then we'll do, kinematics, and then we'll do dynamics. So this is the first midterm, basically. Lagrange is the second midterm. And then you come, and we'll finish this in the piece before the final exams. So I will refer to this slide, this kind of map over and over again, and that'll be a, it'll tell us where we are in the class. If, for those of you who've read Harry Potter, so it's a Marauder's map. And by the way, 2004, which is the follow-up class to this one, picks up here. And 2004 is all about taking the equations of motion. Now you know where equations of equations come from rigid bodies. You can also derive equations of motions for motion, or equations, dynamic equations for solid bodies which are not rigid. You can do it for fluid mechanics. And 2004 deals with now looking at the behavior of these systems expressed in terms of differential equations. Okay, I have one last slide, and I think I have one more slide. Yes, this is the last slide. Now we're going to look at kinematics. The first thing you need to know about kinematics, actually I have 2 slides, is what goes into kinematics. Now in kinematics, we really have only 3 or 4 key concepts. The first key concept is the concept of a position vector. A position vector is fundamental. Whenever you're trying to find the velocity or acceleration of something, you need to ask yourself, what's the position vector, right? It's the basis for everything we do, and we will basically take derivatives of position vectors, and we will build from this. And in fact, if you get this, if you get position vectors and the derivatives of vectors, then everything else I'll do later is just a building block that you can derive from this. So we will concentrate on this, and this will actually be the focus of the next class, the class when I'm back on Monday. We're going to nail this. And the way we're going to nail this is I will describe to you a problem. I'll describe that problem in actually the end of this class as well, verbally, and we will solve it. It's going to be very similar to that problem of the astronaut on the space shuttle as it hurtles around the Earth. And we're going to try and figure out what the accelerations are and the velocities are. So position vectors, then frames of reference. It's just a simplifying building block. And in particular, when you come to kinetics, that is Newton's equations, there's one special frame that we will keep referring to, which is the inertial frame. So we'll talk about frames of reference. Then we'll talk about rotations. It's just another simplifying concept. Angular velocity is actually just a way of taking derivatives, believe it or not. And we'll talk about angular velocities. And it's very useful for rigid bodies. It's also actually useful in fluid mechanics. You have rotation in fluid mechanics as well, but the way you do it there is different. I don't know what the because all bullet is, I'm sorry. But the bottom line after that is we will do constraints. So you can ignore that because all bullet, it wasn't supposed to be there. So this is my last slide. And what I'm going to do now is describe to you what a frame of reference is and what a position vector is. And we're done today. And I'll see you on Monday after this. All right. So here's a question. It's a thought experiment. If I showed you this picture of a particle, it's a dimensionless particle, but I blew it up so that you could see it, P, traversing some trajectory in space. If I showed you this picture and I said, hey, what's the velocity of this particle? How would you figure it out? Think about it for a second. What is the velocity of this particle? Well, if you think about it, it's actually an incomplete question. Can I just say what is the velocity without providing you with some additional information? Let's see. The question you should ask me is, Sanjay, what are you measuring it against? Because a particle doesn't have a velocity by itself. You need to be measuring it against something, right? For example, if I'm trying to track a missile coming in from someone I don't like, I can, for example, consider a ground station, a satellite, a radar, and I could say that I can take a position vector. Remember, we're talking position vectors here, from that radar or from some point fixed on the ground, ROP, which goes from O to P, and I can call the ground and the ground station, which are all stationary with respect to each other, I can call it reference frame A. And I could take the derivative of ROP with respect to time, and that's the velocity of point P with respect to frame A. Right? Now, quick thought experiment here. If instead of point O fixed to that, to the center of that radar, if I picked a point, some other point, O prime, fixed to the ground, such that O and O prime don't move with respect to each other, would the velocity be the same? Well, the position vector would be different, but the velocity, the derivative, would actually be the same. So it doesn't matter where the point of origin is when I'm looking at velocities and accelerations, but the position vector depends on the point of origin in a single frame. So this missile has a certain velocity in this frame. Now let's write it out. And you know what? Let's plunge into some fairly complicated symbology here. The velocity of this particle, this missile in space, as you can see now as I'm going to point at it, is the velocity of missile, the point P. If there were two missiles or two missiles, then I would have to, the other missile would have another velocity. So I need to say this is the velocity of P, okay? And I'm going to write here frame A because, and it'll become obvious why, because the velocity with respect to frame A. And I've also got to say it is, with respect to frame A, it is actually the derivative of position vector of point P with respect to this point O, the derivative with respect to time. So that is the position and velocity, or that's the velocity of point P with respect to frame A is A. With respect to A, the derivative of this vector ROP with respect to time. Now, I might be tracking that same missile from, as you can see on the slide, a different frame of reference. For example, I might have a low Earth satellite tracking these missiles, and the satellite could be moving around the Earth, could be rotating, and the position vector of that satellite of the missile from this satellite, and this point is Q, is RQP. So clearly the velocity that this guy is going to see is going to be different, right? Because this guy is going to measure a different unit vector and different velocity. And that velocity, first of all, we can't call it AVP. By the way, the V here is in bold, right? I put it in bold, or I might use an underline to show it's a vector. R is in bold, or I might put an underline to show a vector. But the velocity of point P with respect to the satellite is obviously not AVP. If we call the satellite frame B, it's going to be B with respect to B, velocity, point P. So it'll be BVP, right? So it's going to be BVP, derivative with respect to frame B of the position vector Q to P, RQP. So what this is telling you is that obviously the frame of reference is important, but there is something known as the frame with respect to which you take the derivative of something. That is a concept that when I'm done with you guys in the next 2 or 3 classes, you will have understood at a very deep level. We will constantly write things in terms of frames. When you look at dynamics, derivatives cannot be defined with respect to time if you do not specify the frame in which you're taking the derivatives. This might seem an ethereal concept, but trust me, we're going to do a problem next week where we will nail it. And if you nail this, the rest of the class is easy. So it's a bit of a tough pill to swallow, but this is going to be the essence of next week, all right? And here's what I'm going to do next week. I'm going to examine a problem in which, consider a frisbee thrown across the room. Consider a spider on that frisbee, and that spider is kind of running on that frisbee. We're going to find out what the acceleration of that spider is with respect to a frame attached to the frisbee and with respect to a frame attached to the ground. And we're going to show they're different, and we're going to show how much they differ and what the terms are. All right, and believe it or not, that's actually the most general situation. We'll do it in full vector notation, and when we nail that, actually, you've understood a lot about kinematics. And everything that follows in this class is going to be about simplifying that and doing that in quicker and more efficient ways. So listen, it's as I said, welcome to 2003. Thank you for taking this class. We'll have a lot of fun, and I'll see you on Monday, and have a great weekend. Sorry I'm not here. Glad we could do this by video, and we'll connect shortly. Thanks. Bye.